Okay, so let's get going here. All right, good to see you guys. It looks like there's about 15 people here, which is pretty good. So yeah, I didn't really have like a super rigid plan for this. I have a few exercises, not that I just sort of like, I don't know. Some of them I kind of like pulled from the internet, and some of them I just sort of came up with. Hold on. But I was definitely intending for at least, roughly half of this time to be dedicated to, answering you guys' questions. So if you have any questions about, problems you found difficult or concepts that you feel like you're having a hard time understanding, um, I think maybe we can start off with that, and then definitely like feel free to keep asking questions if any come to your mind as we go through the stuff. Any questions?
Can we say that like a supremum and infimum exists in any metric space? Because not all of them can have like order or be like countable, I guess.
Right. Yeah.
But can we like use those concepts in proofs?
Yeah. So good question. Yeah. Like what you were saying, not all metric spaces come with the concept of an ordering. So actually, no. No. Most metric spaces are not ordered. Right. So, I mean, obviously, if you take a metric space and you want to talk about, any kind of like set of real numbers that is related to the metric space. So, for example, so like something like okay, yeah, like this. So like sub E does not exist for E subset of a random metric space right? But of course, a lot of these, you know, like for example, the sup of like, you know, the distance from like, you know, S to like S naught for S and E does make sense, right? Because ultimately this set here is actually just a set of real numbers, even though you're sort of like quantifying over elements of a subset of a metric space, right? The fact that the elements of this set end up being real numbers means that you can take this up. So for our purposes, we'll basically say sup and inf only makes sense for sets of real numbers. Okay.
And that means just R, not like RK.
Right. Yeah. So RK does not have like an ordering on it. So yeah. The ordering is like exactly what is necessary to make it so that sup and inf do make sense. So any set that doesn't have an ordering, you automatically like without that, there's just no meaning of sup or inf. Yep. Good question. Any other questions?
Could you explain the solution for 11.5a on the homework?
Sure. Yeah. Hold on. Let me pull it up. Hold on. Let's see. 11.5. Okay. Yeah. Sure. Right. So, okay, this is kind of weird. It's kind of annoying because my. Okay, let me just like minimize the whiteboard for a second. Yeah, and then hold on. Just so I can look at like what I actually wrote here. Right. Okay. Yeah. So basically, the solution here uses like the. You were asking about A, right? Yeah. Right. So the solution uses the denseness property basically. So let's see. So we want to show that the set of subsequential limits of Qn is this closed interval from 0 to 1, where Qn is an enumeration of the rationals in I guess the half open interval like this. Okay, so what this means, remember, is just so for a sequence to be an enumeration of rationals like this just means like every rational number in this interval gets listed off at least one time in the sequence Qn, right? So the way we would show this would be like, okay, you want to show that anything outside of this set is not a subsequential limit, right? That turns out to be easy. So like, suppose, you know, x is less than 0, then like x is not a subsequential limit of Qn because all subsequences of Qn are bounded below by 0, right? So like the limit of any convergent subsequence of Qn has to have a limit that's at least 0. So it can't approach x if x is less than 0. The same thing is true for x greater than 1, right? So so anything outside of this interval is automatically not a subsequential limit. So let's look at things that are in the interval. So like so you know, let's let x be in here, right? Then you know, well, actually, let's just consider the case of like something that's like strictly in the interior. Not that it ends up really mattering. I just don't want to deal with sort of irritating technicalities and stuff. But like, so okay, what the argument we're making is like, okay, for all like k, right? Well, actually, yeah, it's like a little bit more. It's a little bit more subtle. Okay, so let's see how to say this. So okay, we'll choose subsequence Q and K. Oops. As follows. Right. So you know, take I don't know. Right. Okay. So take n1 such that, you know, Qn1 is in like x minus 1, x plus 1, or something like that. So I mean, really, n1 can just be like arbitrary pretty much. But then take n2 such that, and n2 should be bigger than n1, of course, such that Qn2 is in like x minus 1/2, x plus 1/2, right? And so on. Generally, we take nk bigger than nk minus 1, such that Qnk is in x minus 1 over k, x plus 1 over k. So the question the main question is just like, why is this possible, right? And the reason is because like once you get to, you know, for each k, like when you're trying to choose nk, right? The question really is just like, okay, we've chosen things up to like nk minus 1, right? So whatever nk minus 1 is, like we've kind of looked through that many terms of the sequence Qn so far, right? So we've looked at like Q nk minus 1 terms so far, or I mean nk minus 1 terms so far. And then like basically in this interval, right, the interval x minus 1 over k, x plus 1 over k, there have to be like infinitely many rational numbers in this interval, right? So like it can't be possible that every single rational number in this interval between x minus 1 over k and x plus 1 over k appeared already in the sequence, because we only looked at like nk minus 1 terms, right? That's only a finite number of terms. So we couldn't have already exhausted like every rational number in this interval, right? So there has to be a rational number in here that has not been listed off yet in the first nk minus 1 terms. And that's the one, like whatever the index of that one is, that's what we choose as nk, right? So in the end, we end up with a sequence where a subsequence where this is true for each k, basically. And that subsequence has to converge to x because as you let k approach infinity, the distance is, you know, the distance from Qnk to x is at most 1 over k, so that approaches 0, right? So like absolute value of Qnk, sorry, minus x is less than 1 over k for all k, right? And this forces Qnk to approach x. So that shows that x is a subsequential limit of qn for all of these values of x. And then for x equals 0, instead of doing like the symmetric interval, you literally just you do like x or like you do like 0 comma 1 over k instead of like negative 1 over k 1 over k. And for if you look at 1 instead of 0, then you do like 1 minus 1 over k comma 1 here instead of like the symmetric interval, basically. Does that explain? Does that make sense?
Yep.
Yeah, I'm happy to clarify any aspect of this. It does kind of rely on the assumption that we've shown, right, that like in any A, B, there exist infinitely many rationals, right? And like technically the denseness property, we only showed that there exists at least one rational number between any two other numbers, but like it's an immediate consequence of that there actually have to be infinitely many, because like you can just keep getting more and more rational numbers by like looking at, you know, smaller and smaller intervals in between these two numbers, basically. You know, you can look between like a and a plus b over 2, and then like a plus b over 2 and b, or like, you know, whatever. Like you can chop this interval up into thirds or whatever you want to do, and you can get infinitely many rational numbers that way.
Yeah.
So
I just had a quick clarification, so like related to the denseness property. So like if we just chose a subsequence such that like q and k is just equal to x, can we just say?
But the problem is that we don't know if x is rational or not.
Okay. Oh,
Yeah, so it's really specifically when x is not rational that well, I mean, actually, even if x is rational, you're not guaranteed that x will show up in the sequence qn more than once, actually. So you can't build a subsequence that repeats the value x. Even when x is rational, you can't necessarily build a subsequence that repeats the value x infinitely many times, because it might only show up like one time in the sequence, basically.
Got it. Yeah, that makes sense, actually. Yeah, thanks.
Yeah. All right, great. Any other questions?
Yes. Hi, Professor. I actually have some problem. So I was looking at the notes that you have for the alternative solution in the July 1st discussion.
Yeah.
About the problem, like the lim sub of a product is less or equal than the product of two lim sub, right?
Yeah.
And then, like, according to your logic, I was wondering, because like you applied Bolzano-Weierstrass theorem twice in the second solution, and so my question is that in a bounded sequence, can the limit of the convergent subsequent equal to the limit of the sequence?
Sorry, 1 second.
Yeah.
Let me just write some stuff. So, can you say the last bit again?
Yeah. So, like, my question, in a bounded sequence, can the limit of the convergent subsequent equal to the limit of the sequence?
Yeah. I mean, well, so if this exists, right, then actually this must equal this one. So, okay, for convergent sequences Sn, all subsequences converge to the same limit.
Oh, okay.
Right?
Yeah.
And that's actually one of the things that we exploit in that solution, because basically what I did was I found a subsequence, I found like a convergent subsequence of a subsequence of the bigger sequence, right? And then I looked at like the limit of that convergent subsequence, and I said that like the limit of that, like if you take those two convergent subsequences and you multiply them and take the limit of that, it has to be the same thing as like what the original limit was of the convergent subsequence of SNTN, basically. And that's using this fact. Yeah.
Oh, okay.
Yeah.
Okay. So like if we want to show the limit of the suprema of a thing, of a sequence, we just try to show, we just prove the limit of the convergent subsequent of it, right?
Yeah, like, okay, so the overall logic was like, okay, this is like a general thing here. So it's like, okay, if you want to show, if we want to show for like a general sequence that lim sub Sn is less than or equal to like x for some number x, right? We can let Snk be an arbitrary convergent subsequence and show that Snk, that the limit of Snk is less than or equal to x. So basically, because what this does, right, the reason for this, the reason for this is that the lim sup of Sn is the supremum of the set of subsequential limits, right?
Yeah.
So basically what we're doing is like over here, when we make this argument, right, let Snk be an arbitrary convergent subsequence and show the limit is less than or equal to x, what that shows is that x is an upper bound on the set of subsequential limits, right? Because exactly. Okay. Yeah, I think I actually never really like explicitly delved into this idea, like why we make arguments this way. Yeah, it's because of this. So basically it's like really the idea is really like, okay, let S be a subsequential limit of Sn, show S is less than or equal to x, right? That's showing that x is an upper bound on the set of subsequential limits, right? And so, but then it's like when you let S be a subsequential limit, it's really the same thing as like letting Snk be an arbitrary convergent subsequence, basically. So this, because like if you let a number be a subsequential limit, like a number is only a subsequential limit if there exists a convergent subsequence approaching that number, right? So that's like why this is the same thing, really.
Okay, got it. Thank you.
So this is the same as letting Snk be any convergent, key emphasis on convergent, convergent subsequence. Yep.
Okay, got it.
Yeah, very good. Is there another question? Oh, let me actually, hold on. Let me pull up the like participant list. Whoa.
Oh, Professor, I actually have another question. So like in the lecture of monotonic subsequence, you mentioned that if there exists finitely many dominant terms, we have to find increasing subsequent. But like if there exists infinite dominant terms, we find a decreasing subsequence. So I just wonder, like, what does that mean?
Right. So basically, okay, so for an arbitrary sequence Sn, like we aren't guaranteed to find an increasing subsequence, right?
Yeah.
And the same goes for a decreasing subsequence, right? The only thing that we're guaranteed, just, you know, at least one of those, right? So we're guaranteed to either be able to find an increasing or a decreasing subsequence at least. Sometimes you can actually find both, right? But we're at least guaranteed to be able to find at least one of these two types of subsequences, right? So like the condition of, so it's like, how would you tell which one you're looking for, basically, right? That's kind of like what this condition of like dominant, like how many dominant terms there are is supposed to be doing, is like, you know, so if there are infinitely many dominant terms, then we know we can find a decreasing subsequence. If only finitely many, then we can find an increasing subsequence. That's all it's meant to do, is just like it's just a rephrasing sort of, well, not exactly a rephrasing, but like if you imagine trying to think about like, okay, the condition, like basically saying that there does not exist a decreasing subsequence of the given sequence. It's not the same as saying that there are only finitely many dominant terms, but it's like similar, I guess, if that makes sense. Yeah, it's hard to explain like where.
Could you please draw it out?
Sure, I can try, yeah. So like, let me think. So let's see. The dominant terms are the things that are bigger than everything that comes after them. So like something like, okay. Let's see. Actually, say that, and like, okay, something like this. I don't know. So the idea is like, okay, so like, let's pick out some dominant terms, at least what look to be dominant terms from the graph. So this would be like a dominant term. And then like this would be a dominant term. These would all be dominant terms. Okay, let's actually put one term here. Oops. So if I just put a term there, then that makes this one not be dominant. But then, you know, this one would be dominant. And then like this one and this one would be dominant, right?
Yeah.
So, you know, they're decreasing because like, if this is dominant, it has to be bigger than all of the ones after it, right? And then if this is dominant, like it has to be bigger than all the ones after that. And if this one's dominant, right, they're each bigger than the next one because the next one comes after. So for this to be dominant, it has to be bigger by definition, right? So if you can just keep finding these points forever, then you get a decreasing subsequence that way, right?
Oh, okay.
So the problem happens when you can't find enough of these points, right? So like, you know, it's easy to think of sequences where actually there are only like where there are like no dominant terms, right? Oh, I still have a red. Oops. Right. And I mean, any increasing sequence will have no dominant terms, right? But even like, okay, let's say we do something like this, and then like, I don't know, that, then like the second term here could be dominant if there's like a, let's say there's sort of an asymptote going this way, right?
Yeah.
The second term here is dominant, but there's only one, right? There's only one dominant term here. And then of course it's easy to see that like if this keeps increasing like this, then you can just take this as your subsequence, right?
Yes.
But it turns out that if there are only a finite number of dominant terms, then you have to be able to find some increasing subsequence, you know, somehow or another, basically. So that's,
gotcha.
yeah.
Yes.
Stepping
Thank
through the
you.
argument in the proof carefully will probably, that's probably like the best way to see why that's true, I guess. It's hard, it's a lot harder for me to like draw why that argument works in that case, I guess. Yeah.
Okay.
But yeah, actually, like, so, you know, it's not this, it's not, just to be clear, it's not necessary that there be like only finitely many dominant terms for their, you know, like it's not equivalent. Okay, so like if you think of it as, if you look at an example of a sequence that's like, you know, this or something, right? Then, you know, there's clearly an increasing and a decreasing subsequence. And there are also no dominant terms for this sequence. So like this would be, you know, increasing, and this is decreasing subsequences, right? But there are no dominant terms. So it's really like, specifically, it's just useful for the proof. It's not the same. It's like having a finite number of dominant terms is not the same as not having a decreasing sequence, I guess is what I'm trying to say. It's possible to still have like a decreasing subsequence and have only a finite number of dominant terms.
Okay.
All right, great. Any other questions? These are good.
Is there a way for us to construct a closed and bounded set, but not compact?
Not in the normal real number system, no. Because that's that's like the Heine-Borel theorem, is that it says that, you know, all closed and bounded sets of the real, you know, of the real line with the usual metric on it have to be compact. Yeah. But there are other metric spaces where it's possible to construct closed and bounded sets which are not compact. Like one of the most important examples of this, and it's like a little bit hard to understand probably, but it would be like for example, so we haven't really defined continuity, but like the set of continuous functions on 0, 1, and then like the metric on S would be, you take your two functions and look at the maximum of the difference then like any like I'm pretty sure that, so then like, you know, take, you know, E is the set of like functions in S such that like absolute value of f of x is less than or equal to 1, for example. Then E is bounded and closed, but I'm pretty sure not compact. Okay, but that's because like the metric space we're dealing with here is like completely like different and crazy. Like the elements of this metric space are functions, right?
Yeah.
So like one of the reasons that this kind of thing can happen is when you deal with spaces that are in some sense like infinite dimensional. And this is an example of a space that's actually like infinite dimensional in some sense, although we haven't really defined that. So, but yeah, I mean, there are metric spaces where this is true.
Okay.
Actually, an even more like simple example, this is kind of important, but so like you could take like, so let S be like just the set 0, 1 as a subset of R, right? With dxy equals x minus y, right? Then S itself is closed in S, obviously, and bounded, but not compact. So this is like a subtlety of how, so I think I tried to explain this before, and I'm not sure how good of a job I did, but basically, right, even though S is not a closed set in the real numbers, right? Like if you look at R itself as a metric space, S is definitely not closed because it's missing the point 0 and 1, right?
Yeah.
But the thing is that if you just restrict your attention to S and consider it like its own metric space, right? So basically you just like ignore the existence of any numbers outside of this interval, right? Just like forget that R exists completely. And only look at this interval, it's still a perfectly good metric space because, I mean, we can define a metric on it, right? And we can take any two numbers from this interval and calculate the distance between them according to this metric. So S is a perfectly good metric space. And we know that like for any metric space S, then the set S itself as a subset of itself always has to be closed, right? Because the empty set is always open. So like S is the complement of the empty set in itself. So S has to be closed as a subset of itself, right? S is closed in S, and it's bounded just because like, you know, the maximum distance between any two things here is 1, right? So so it is closed and bounded, but it's not compact because you can actually take an open cover, much like the one that I drew in the picture in that lecture, where I showed like an open cover of the interval 0, 1 that does not have a finite subcover. You can take that same open cover and use it in S itself, and you'll end up with an open cover that has no finite subcover. So S is not compact in itself. Yeah. Even though it's still closed and bounded, right? As weird as that may seem. It's just like a technicality. It's a technicality that comes from considering S as a subspace, basically.
So it's very it's very important for us to highlight the domain because.
Yeah, exactly. Like to be aware of what the ambient space is, basically, right? Yeah. So like if S, like when you're looking at S as the ambient space, then whether or not the set 0, 1 is closed changes based on like what the larger metric space is. Yeah. Yeah.
Okay, got it. Thank you.
Yeah, this is like, it's really hard to exactly explain this. And I feel like it's something that's commonly, you know, it commonly trips people up when they first learn about this kind of thing. So definitely, you know, it's good to pay attention to this nuance. So any other questions? Okay. Well, we can look at some of the problems that I came up with. So let's see. What would be a good one? Let's start off with something fairly like routine, I think. So show, or like, show directly from the definition that the sequence let's see, what did I have? Oh yeah, so like n to the fifth plus n sine of n over n to the fifth. Oh yeah, 2n to the fifth minus n squared plus 7 converges. Okay, so I think for the purposes of the review session, I think I'm just going to let you guys work on this stuff individually, just because I think it's important. Like if you're trying to practice for the exam, if you're really trying to review for the exam, you should be able to be like solving the stuff on your own. So I'm going to give you guys like about, let's say 10 minutes to work on this, and then I'll go over it. So we can resume at 5:55. Okay.
Um,
All right, so let's look at this. So, the first order of business when dealing with a problem like this is determining like what you think the limit should be. And fortunately, right, in this case, it's hopefully not too difficult to see that we should expect the limit to be 2, right? Because basically in the numerator, we have this like n to the 5th term, and then in the denominator, we have n to the 5th. And in both cases, those are sort of like the dominant terms in the respective, expressions here. So it should just be sort of the ratio of those coefficients of the dominant terms that determines the limit. So we expect. So let's just say we want to show now that this converges to 2, right? So what we want to do is we want to sort of pick big N so that so 2n to the 5th plus n sine of n over n to the 5th minus n squared plus 7. Sorry, whoops. Minus 2 is less than epsilon, right? And so once you simplify this inside, so this is the sort of the leading term in the numerator should cancel out here. So we end up with like a 2n squared plus n sine of n and minus 14, I believe, over n to the 5th minus n squared plus 7, right? Okay, so now here's where the kind of slightly tricky business comes in, okay? And I know because I glanced at a couple of your homeworks too, and I know a lot of people really like to take things like this and then try to solve for n or something, but you really should not be doing that. So like in this case, it's actually literally impossible to solve for n because of this like n sine of n term. But really, like, even if it were somehow possible and it was like this complicated expression, it's just not a good method. Okay, so what you should be trying to do is basically trying to bound this expression above by simpler and simpler and simpler expressions, right? So let me maybe make a new page here. So I want to bound you know, this 2n squared plus n sine of n minus 14 over n to the 5th minus n squared plus 7, I believe, right? So how do we do that? Right, okay. The game, it's kind of a little game of estimates and stuff. So first, like, I think generally, I don't know, for me, like the first thing I always do is just like apply the triangle inequality to the numerator. So we can say that, you know, so let's call this, I don't know, star. So star is less than or equal to the absolute value of 2n squared over n to the 5th minus n squared plus 7. And then plus the absolute value of n sine of n over n to the 5th minus n squared plus 7, plus the absolute value of, and I can just delete the minus sign here because it doesn't matter. Okay, great. Right, and then what you can say is like, okay, so for sufficiently large values of n, right, the denominator down here is positive, okay, for large enough n, like for n bigger than, I don't know, probably like 2 or 3, maybe 4 at the most or something like that, right? I don't know exactly what it is. It doesn't really matter. But so for sufficiently large n, this is positive, and then we can make the overall value bigger by like decreasing the value of the denominator. So for example, right, well, for one thing, just eliminating the 7, right, that's a valid thing to do to preserve the inequality, right? So we can do like 2n squared over like n to the 5th minus n squared, plus like n sine of n over n to the 5th minus n squared plus 14 over n to the 5th minus n squared. Okay, and then, I mean, if you want, you could like cancel powers of n or something. Well, that'll happen eventually. It doesn't really matter when you do it, I guess. And then, but then like the other thing is, okay, so we can't just like delete this like negative n squared, right? Because that would actually increase the value down here. And we're only allowed to like decrease the value down here. So what the trick that I usually use for this is just like replace this term with like a smaller multiple of the dominant term, basically. So like you could say like for sufficiently large n squared is less than like n to the 5th over 2, for instance, right? So by replacing n squared with n to the 5th over 2, you actually decrease the value of the denominator, thus increasing the overall value, right? So this would be like less than or equal to 2n squared over n to the 5th minus like n to the 5th over 2, right? N sine of n over n to the 5th minus like n to the 5th over 2. I guess maybe it would be more efficient to do this stuff with the denominator first and then use the triangle inequality at the end. It doesn't really matter.
Wait, question.
Uh-huh.
Wouldn't adding wouldn't n to the fifth over 2 be greater than n squared for a large n?
Exactly. Yeah.
And then the denominator becomes smaller?
Exactly. So the overall value becomes bigger.
Oh, okay.
Yeah.
Got it.
Yeah.
Thank you.
Yeah. Sometimes like it's so easy to like lose track of how many times you flip the direction that you're moving, because like the operation you do, like we wanted something bigger than this so that this would be smaller so that like the whole thing would be bigger, right? It like, I don't know, it's easy to like lose track of that. You just have to be disciplined, I guess, or careful. I don't know. But yeah, so when you have like a negative term down here, you can always just like make it bigger, I guess. And usually the way I do that is just like make it combine with like the biggest term. So then this is just like, you know, I don't know. At this point, it becomes something really, well, okay, actually, let me, oh, whoops. Let's see, okay, so this becomes like n to the fifth over 2. So you'll get like a 4n squared over n to the fifth. And then that's the same as 4 over n cubed. And we can also drop the absolute values now because everything becomes, well, at least for, except for this one, but so we'll have like a 4 over n cubed plus like, and then this is like less than or equal to like absolute value of n on the top, right? So we can make this be less than or equal to like, and then like n over like n to the fifth 2. So that's like 2n over n to the fifth, which is 2 over n to the fourth. And then we'll have one more term, which is just like 14 over n to the fifth, I guess. I don't know. Or like 28, I guess. 28 over n to the fifth. Right. And then it's just like, okay, I mean, you can bound all of these above by like something over, like you can just replace these n here with like n cubed actually. So you could just get like 4 plus 2 plus 28 is 34. So 34 over n cubed. There you go. So then you can use like 34 over n cubed. We basically just showed like for sufficiently large n that star is less than or equal to like 34 over n cubed. So okay. So then you can just use this as a way to like calculate your value of capital N, right? Like just, you know, set that equal to like epsilon and then solve for little n or something, and you'll get like, you know, the cube root of 34 over epsilon or something like that. Yeah, so we can take n, you know, n equals the cube root of, I believe, 34 over epsilon. And then the preceding logic shows that which is what we want to do, right? Like star is less than, you know, well, it's less than, you know, 34 over n cubed, which in turn is, I guess, less than epsilon by our choice of capital N, right? So anyway, yeah, it's just like these, you know, they can just get like more and more complicated, and in the end, it just ends up being like the same algorithm for a lot of them, at least when you're dealing with stuff that's like mostly polynomials with maybe some like random bounded functions thrown in, you know. If you throw in like exponential functions, things can get slightly more weird, but not that much weirder than this. Like you can do a lot of the same stuff. So anyway, any questions about that? Oh yeah. Let's see a question.
I was wondering if we had a question like this on the exam, would it be sufficient to just like have a chain of inequalities without any explanation?
As long as like getting from each thing to the next is like obvious, I guess. Yeah.
Mhm.
Just don't like bundle up like 10 steps of algebra in the same thing or whatever, you know.
Yeah.
Yeah.
Oh, also, Professor, I wonder, could you please tell us some more about the exam? Like, when will we have the exam paper, and then like,
Yeah,
How-
yeah. So
yeah.
I'm aiming to post it at midnight tonight. If it's not posted at exactly midnight, although I think it will be, it's not going to be too hard for me to actually. I have most of the questions already picked out, and I just have to like write it up, I think. So it should be posted at midnight, and then it'll just be like whenever it gets posted. So most likely midnight. It'll be due like 24 hours from that point, and it'll be basically like the format will be roughly like, okay, there might be some questions at the beginning that you're basically sort of like required to answer, and then there'll be some collection of questions where it's like choose like some number of these out of the total to answer. So maybe like, you know, choose like 5 of the following 7 questions to answer or something like that, right? And a lot of them will just kind of be these like prove or disprove statements. Yeah, I don't know. It's going to be, yeah, that's about as much as I want to say about it right now. The questions will probably generally be weighted about equally, and hopefully, like I'm taking some pains to make sure that they're not like easy to Google and stuff, and that like if you do Google them, like if people Google the questions, I think it'll generally be like, from what I can tell, it'll probably be obvious from what they write down that they Googled the question. Especially because for some of them, actually, if you Google them, like for some of the questions I designed, if you Google them, you'll get like misleading results. So we'll see. But yeah, anyway, so they should be sort of like ungoogleable, basically. And they're going to be a little bit challenging, but you know, obviously, if the distribution is low, then you know there'll be effectively a curve. The exam will not be curved downward, to be clear. Okay, if everyone does really well on the exam, then that's just like the way things are. I'm not going to like try to force a certain distribution or anything. But if it's a low scoring exam, then like definitely, you know, obviously the standards will be adjusted accordingly. Yeah. Does that answer your questions?
Yes. Thank
Yeah.
you.
Wait, how long do you expect the exam to take for like an average student?
Yeah, like a couple hours, like maybe three hours or something, 3 or 4. It kind of depends on like, yeah, I don't know. Average student. I guess I don't know. I really don't know. Because it depends on like the sort of level of like, I mean, yeah, I don't know. I think to get a perfect score, I guess, if that's what you're like asking about, like it'll be hard. It'll be like very hard to get a perfect score, I think.
Yeah.
Or like compared to the homework, like the length and the difficulty of the exam compared to the homework.
It'll be like shorter in the sense that there'll probably be like fewer problems, but it will be, but I think the hardest problems on the exam will be like about the same difficulty as like the hardest problems on the homework, or maybe slightly harder.
Okay.
Yeah. There are going to be some hard problems on there. I'm sorry. I have to do it. My hands are tied here. But yeah. Just try not to like worry too much. Just like, do your best, and like if you've I guarantee, like, if you've been following along and paying attention to the homeworks and the solutions and the lectures and everything, like, you will definitely be able to get like a solid score on the exam. Okay. without like extreme pain. You won't have to like spend all day on the exam just to get like a passing grade if you've been doing the work so far and everything. Okay. Anyway, we'll see. I don't know. Yeah, we'll see. Let's see. Let's maybe look at another problem here, unless there are more questions. Okay. Let's try. Here's kind of a simple one, but maybe like a little bit tricky in some sense. So give an example of let's say a chain of closed sets F1, F2, so an infinite descending chain of closed sets in R, such that the intersection n equals 1 to infinity of Fn equals the empty set. Okay. So I think maybe we can take about 5 minutes on this one. Yeah. It's not super long, but it's maybe a good mental exercise here. Hey, sorry. Okay. My Zoom like glitched really bad for some reason. All right. Okay, here we go. Great. Okay. So let's see. Right. Okay. So this was not meant to be. It shouldn't be like overly complicated or anything. But it might be. I don't know. It's easy to kind of go down the wrong path mentally with this. What you should remember is that, like, okay, what do we know about things like this, right? We have a theorem that says if all the Fn are bounded, and obviously we're, since we're assuming they're closed, right? Then if we make all of them closed and bounded, right? So closed. If we make all of them closed and bounded, then the intersection is guaranteed non-empty, right? So that's a bad. We shouldn't be. They have to be unbounded, basically. Yeah. In fact, I think that means that literally every single one of them has to be unbounded. So how do we use unbounded sets to do this? Well, I don't know. A common way to do it would just be like, f n equals like n infinity or something, right? So then, for all x in R, eventually n is greater than x, so x is not in n infinity, and there you go, right? So the intersection of all these like sort of these like rays out to infinity as the endpoint here keeps moving further and further out, that intersection ends up being empty. Okay, any questions about that?
Can we also just say that all Fn's are empty, the empty set?
Oh yeah, I forgot to make them be non-empty. So yeah, technically that's a valid solution the way it was phrased. Very good attention to detail. But yeah, I meant for them to be non-empty. So yeah. Any other questions?
Can you have a set that is bounded but not closed? And
yeah, I mean, there do exist sets like that if that's what you're asking. Like something
right,
like,
I mean, for this example.
Right. So you're saying, oh, bound. Okay, like a chain of sets that are bounded but not closed, where their intersection is empty.
Yeah, that's my question.
Yeah.
Okay.
That is a good question, and the answer should be yes. I mean, yes. The answer is yes. Let me just think for a second. Oh yeah. I mean, something like 0, 1 over n open intervals will work for that. Because yeah, I mean, for any like obviously 0 is not in it, right? So 0 is not in the intersection. Negative numbers are obviously not in the intersection. And then for any positive number, eventually this gets too small. So a positive number will get thrown out eventually. Yeah.
But we're looking for the intersection of the chain of closed set, right? So can we still use 0?
Right. Yeah, so that was the original problem. In the original problem, they had to be closed. So that's why we ended up with this here. But
Okay.
then in this question, someone was asking like, so these are all bounded, but not closed, right? So it's kind of basically the flip of this question, where here it's like, what happens? Basically, it's like we're asking what happens to the theorem, like theorem, I don't know, 14 or 13.5 or something, I don't remember. That theorem from section 13, what happens if we drop either of the two assumptions? So this question here was like, what if we drop the assumption that they're bounded, right? And then the other one over here is like, what if we drop the assumption that they're closed? So now we have these non-closed sets, but they're still contained in each other, right? And they're bounded. They're all bounded, but their intersection is 0, is the empty set. Sorry. Was that your question? Sorry.
Oh, wait, Professor, could you explain a little bit, like for all x belongs to the real number, eventually when n is greater than x,
yeah,
like what does that mean?
Well, it just means that like n just keeps increasing, right? I mean, for each n, like it literally just increases and gets arbitrarily big, right? So no matter what x we look at in R, like once we look at I mean, there exist large enough values of n that they're bigger than x, right? And then once n is bigger than x, then x isn't in this set anymore, right?
Oh, okay.
So x is not in the intersection, right? So this is the set Fn. So as soon as a number fails to be in even a single one of these, then it's not allowed to be in the intersection, right? So all I'm saying here, I mean, this is like, you barely even have to say this, right? Like it's so obvious that you might as well, you know, you can just say like, okay, for all x, there exists an n greater than x. So for that n, right, x is not in the set. Yeah.
Yes.
Professor, I have kind of a general question. Apart from just like having watched the lectures and read through the important theorems in the book, like what would you say is good prep right now in the last evening before the exam?
Yeah. Actually, like, I would say like reviewing the homeworks and the solutions is definitely a good idea. Like making sure, like reading the solutions carefully and then kind of like comparing them to what you did very carefully, right? Like kind of like step by step, seeing what the differences are, right? Obviously, sometimes like there'll be differences between what you did and what's written in the solutions that are like okay, right? Because there are like multiple ways to kind of like, you know, well, there are multiple solutions to a lot of the problems. In fact, sometimes some of the solutions look pretty different from each other, but like that doesn't stop you from sort of looking at the two solutions and being like, okay, like, are there ideas in my solution which are like more cleanly encapsulated in the actual solutions, for example, or like is what I did like completely different from what's in the solutions? And like also just very critically looking at what you did and being like, is every step here correct or whatever, and trying to think very carefully about that. I mean, I guess if you're really in a situation where you're looking at your solution and it's like utterly different from what's in the solutions that I posted, then it's kind of hard to like see whether you might have gone wrong somewhere or whether what you did is actually right, unless, you know, like unless you're sort of really careful and like think really hard about it. But if what you did is sort of like roughly similar to what's in the solutions, then you can kind of look at them and be like, okay, you know, what could I have like done better about this, or you know, or maybe if you came up with like a cleaner way of doing something than what's in the solutions, you know, then write me an email or something. But I think what I post is generally like close to like the optimal solutions for all the problems, basically. So there are some like useful techniques in there, I think. Yeah, I don't know, kind of rambling, but yeah, I do think that like looking very closely at the homework solutions and doing that comparison is really helpful.
And on that note, are we expected to do extra practice on our own? So sometimes I find solving problems unsuccessful. And it's rather easy to read a proof given by the book and understand it. But it's more challenging when having to come up with an original proof.
Right. Yeah. Yeah. I mean, that's definitely the problem. I would say like, so as far as the question of like, are you expected to do more practice on your own? I would say no. I don't expect anyone to do that, although obviously I won't discourage it. But I think that like the stuff you do, the things you're exposed to in the homework, in the homeworks and in the lectures, between those two things, like there, and in, I guess in the discussion sessions too, if you go to those or if you watch the videos for those, between all three of those things, like that should be enough for you to see, at least like be exposed to all the like ideas and techniques that are necessary to do well in the class, I think. That said, I mean, yeah, again, like you could benefit from extra practice. Probably anyone could benefit from extra practice. So, you know, I won't discourage that. When it comes to like extra practice, if you're like, yeah, if you're having a hard time doing it like on your own, one thing you could do is like, if you find a problem somewhere and you try to do it and maybe you start having a hard time doing it, that's like a perfect thing to try to post on like Piazza or something. And like, I'll do my best to help out with it, or you know, hope maybe your classmates will chime in or something like that. I think that would be great actually, if people were like finding extra practice to do, you know, they can bring it to everyone that way. You know, you could work on it a bit on your own and then you could like post it or something and people could talk about it. That could be great. Or if you can find a solution to what you're looking at, then, you know, you can do the same process of kind of like trying it yourself and then looking at the solution and being like, okay, where did I go wrong or something? If you have a hard time solving it.
Okay, thank you. But do you think that doing extra practice would help somebody get better at solving these homework and exam problems?
Yeah, I would say, yeah, I think so. You know, it's hard, like the question is starting to verge on the topic of like, what is the actual nature of the skill of like formulating mathematical arguments, and like how do people learn it, right? And it's like, I'm not even really qualified to talk about like the extent to which people can learn to, you know, generate novel arguments, I guess, in sort of the most general sense. Like I can't really say anything about that topic. But like, what I will say is that, okay, for one thing, in analysis specifically, there are a lot of like techniques and arguments and stuff, like little ideas that get repeated over and over again, like across different proofs, basically. So like definitely doing more and more proofs and more problems and stuff will start to like help you internalize these like little building blocks, right? They're like little building blocks of your argument that it's good to have at your fingertips, right? Like once you do them enough, once you see them enough, you start to like automatically generate them. And they're like not super complicated, but they're also not like trivial either, right? Like something really simple, like, okay, if a number is like not the least, if a number is not an upper bound of a set, then there exists an element of the set which is bigger than the number or something like that, right? I mean, that's a very simple example, but it is something that like when people are first exposed to that idea, even just understanding it the first time can take a little bit of effort, let alone like making that realization, you know, that maybe in the course of like solving some problem, maybe that's a fact that you want to exploit somewhere, right? Like maybe it's a relevant fact. It's not going to jump into your mind as a relevant fact if you like if you're not comfortable enough with it, basically. So like there are these little things, or like when a you know, just the idea that like when you know a sequence converges to a number, you can sort of force it to be however close to that number you want. And like in particular, you can make sure that it stays far away from like other certain numbers or whatever, right? Different numbers besides the limit, you can like force it to be like far away from those numbers, I guess, or something like that, right? Like there are like themes that keep coming up. And so the more problems you do, the better you'll internalize those themes, and then the more you'll be able to kind of like, you know, use them and sort of follow the logic more easily in more problems that you do. Yeah. Other questions? Yeah.
Oh, I had a question about like the FN that you gave for the solution. Like, I get why the bottom part is closed, but why is it that the infinity side is closed as well?
Right. So yeah, the thing is like, infinity is not an element of R, right? So like, we don't want to put a square bracket here. I mean, it wouldn't even really make sense to put a square bracket here, just because like, we want to consider this a subset of R. So like putting a square bracket, it's like trying to imply that you need to include the point infinity. But we don't want to, because it's like not in R. But if you want to think about like, okay, why is this closed, right? Like, so why is, right? By definition, right, what does it mean to be closed? It means to be the complement of an open set, right? So the complement of this is just, right, which is pretty clearly open.
Yeah.
So yeah, you can kind of, looking at it this way, I think it makes more sense. Yeah. But like, again, remember that like, you know, like the way we use the term closed, like closed intervals, it's like they're only called that because they're closed, like A, B are closed when like A and B are finite. Like this you couldn't actually, this like you wouldn't even want to call it half open, or whatever. I mean, yeah, I don't know. They're just like using the terminology of like open or closed interval almost doesn't make sense for an interval like this when it's like unbounded on one side, I guess. Yeah, I don't know. But yeah, hopefully at least this kind of helps.
For sure. Yeah, it does. Yep. Thank you.
Mm-hmm. So about closed intervals, this is kind of a question about the homework. We talked about closed intervals like last week, before we got into anything about the metric spaces, with the subsequential limits being also in the set, and then we have a new definition now.
Right.
So when can we use like either one?
Yeah. So basically, like you can use either one actually, because proposition 13.9 is what tells us that like the old definition, right, is like, okay, the old definition, of, oh my God, of a closed subset of R was that like S subset R is closed if and only if it contains, if and only if it contains all limits of sequences in S, right? That was the old definition. Then the new definition was the sort of metric space topology one. But basically proposition 13.9 tells us that the old definition is equivalent to the new one for R itself, right? So if you take the new definition of open and closed, like the definition from section 13, and you apply it to R specifically, what you'll find is that the closed sets you get that way are exactly the same as the closed sets that satisfy this older definition, basically, right? I think that's like part, dang it, I don't remember, part C or something, part D maybe, I don't remember it. But basically, so yeah, like you can, by invoking proposition 13.9, you could start with whichever definition you want if you're dealing with sets of real numbers specifically, right? You can start with whichever one you want and then just say like, okay, by proposition 13.9, like it doesn't matter. It doesn't matter which definition you start with, basically. Yeah. I guess like unless the problem specifically asks you to like use a specific definition and not use proposition 13.9 or something. I don't know. Does that answer your question?
Yeah, thank you.
Okay, yeah, great. So yeah, you can basically, the answer in short is that you can like pretty much use either one whenever. Yeah. Okay. Are there more questions?
Oh, yes, Professor. I do have a question. I wonder, could you please explain something about De Morgan's law? Because I know that we have a homework question.
Sure. Mm-hmm.
Yeah.
Right. So De Morgan's laws. Let's see. So like, I'm just going to give them to you in a little bit of a simplified way. So let's say A and B are subsets of C, right? Then basically the complement of the union of A is the intersection of, the intersection of the complements. Right, and the complement of the intersection, is the union of the complements. And the common sort of way of explaining this is, let's say we have you know, you can make sort of a little Venn diagram here. Right. So let's say this is A, and this is B, and then this is C. Here's A and B. Right. So if you take the union of A and B, right, then you get, let's see, is there, oh, actually, hold on. There's a nice sort of a tool here I can use. So let's say we have like, I don't know. And then, something like that. And okay, so right. So let's say the you know, the red one is A, and then the blue one is B, right? And the idea is just like, okay, if you take the union, right, that's all of the, that's both areas, the areas of both colors, right? So the complement of that, right, would be the same thing as if you just took the everything outside the blue circle, right, and then everything outside the red circle, and just looked at the things that were outside both of them, basically, right? So you'd intersect everything outside of the blue circle with everything outside of the red circle. So this becomes C without the complement of A union B, right? But in this case, right, so that's when we basically we're looking at everything outside of this set, right? In this case, in the second one, we're looking at the complement of the intersection, right? So in this case, everything outside of the intersection is basically the union of everything outside of the red circle and everything outside of the blue circle, right? So you can get stuff that's either in the red circle and not in the blue circle, or stuff that's in the blue circle or not in the red circle, or both, right? But not things that are in both of them, basically, right? So that's kind of the idea behind De Morgan's laws, if that helps.
Yeah, definitely.
That's at least that's the case of two sets, but then it just sort of generalizes to like any number of sets. You just get the same thing where you can like take the complement of the union of all of them, or you can take the intersection of all of their complements, right?
Mm-hmm.
And then the same thing for the other direction, I guess. Yeah, and it's also like, it can also be helpful to phrase, to like actually like use the, like say in words what this is, right? This is like things, oops. Not in either A or B, right? And then on here, it's like things not in A and not in B, right?
Mm-hmm.
On this side. So it's like, it's really the same thing, actually. Like if you're not allowed to be in either of them, then you have to be not in one of them and not in the other one, right? Anyway, so same concept here. Okay, so that's De Morgan's laws. Any other questions? Okay, in the last 10 minutes or so, oh yeah, here's a good one. All right, oops. So let Sn be a sequence of real numbers, and suppose every subsequence of Sn has a subsequence converging to some, well, let's say, okay, and suppose there exists a number S in R such that every subsequence of Sn has a subsequence converging to S. So there's just one number S, basically, right? There's like some special number S in R, and Sn is this sequence so that no matter what subsequence you pick, there's a subsequence of that one which converges to S, okay? Then show that Sn converges to S. And I want to tell you, you can do this without doing any epsilons or capital N's or anything. There's actually a pretty simple argument in just like a couple sentences that'll explain why this is true. So let's say resume at, I don't know, 6:57, let's say. All right, so here's sort of the very simple argument for this. So we can say clearly, well, actually, say this. So let capital S be the set of subsequential limits, right? Then, so clearly S is in capital S, right? That's just because, I mean, if every subsequence has a subsequence converging to S, then clearly there are subsequences of the original sequence that converge to S. I mean, you can actually just take the entire sequence as a subsequence of itself, and then this hypothesis tells you that there has to be a subsequence of that converging to S. So clearly there's a subsequence converging to S, so it's in the set of subsequential limits. Now let's just show there's nothing else in the set of subsequential limits, right? So suppose, for contradiction, that there exists a T and S with T not equal to S, right? Then there exists a subsequence SNK with SNK converging to T as K converges to infinity, but no subsequence of this can converge to S, right? That violates our assumption that every subsequence of Sn has to have another subsequence of itself that converges to S. If you take a subsequence that converges to a different number, there's no subsequence of that converges to S, because all of the subsequences of this subsequence have to converge to T, right? So that means that S is the only element, right? So S equals just little s. So Sn converges to S, right? That's a theorem, I guess. Well, I don't know. Yeah. So it's just using the set of subsequential limits here. Any questions about that?
I'm a little bit confused about the case where you might have the subsequence diverge to infinity.
Well, then, so, okay, right, yeah, that's actually a good point. So, well, actually, in this case, like, T can actually stand for infinity, and it doesn't really break the argument, because if you think about it, right, so let's suppose T is infinity, then there exists a subsequence diverging to infinity, right? But any subsequence of a sequence that diverges to infinity also has to diverge to infinity. That's like there's a similar fact about sequences that diverge to infinity, or negative infinity, which is that any subsequence of a sequence that diverges to plus or minus infinity also has to diverge to plus or minus infinity. So in that case, it would still be the case that there are no subsequences that converge to S, I guess. Does that make sense?
I just don't remember that, I guess, super well, so.
Sure, okay, so, oh wow, I actually ran out of like pages.
I can just look for it.
Maybe just think about it
believe
yourself,
you, but
or look for it, yeah. It's not, you can actually prove it probably in a line or two, so, yeah. Because like the picture in your head should just be like the overall sequence is being forced to run off to infinity, right? And it can't like consistently dip back down, to some like other range of numbers. It has to eventually get really, really big, right? So if you have any subsequence of that, that's just like, it still has to run off to infinity, because the terms in the subsequence keep getting farther and farther out in the original sequence. Yeah. So
you go ahead.
Okay, this is just a follow-up question. What if you try and assume that the sequence doesn't converge at all?
assume that the original sequence doesn't
Yeah.
converge? So like that would be sort of a contradiction assumption, is what you're saying?
Then if Sn didn't converge, could this?
Because we're just trying to prove that Sn converges, right? So like if
okay,
this,
right, yeah.
if Sn has to converge based on this stuff, you can't really assume it doesn't unless you're trying to prove by contradiction.
Wait, so how do you prove the case that if Sn doesn't converge, or like if Sn doesn't converge to anything, then there doesn't exist a subsequence converging to S?
Well, so we're not examining cases of whether Sn itself converges to anything. We're not making any assumptions here about whether Sn converges or diverges. We're saying that, like, okay, if there was a different subsequential limit, anything besides S, right, then a subsequence that actually approaches that limit violates the assumption up here, right, that every subsequence has a subsequence converging to S. So what we're saying is that there are no alternative subsequential limits. Are you saying, like, what happens if SNK doesn't converge?
So I'm saying, like, let's say if we approach the problem differently and show that if Sn does not converge to S, then there does not exist a subsequence of every, for every subsequence, there doesn't exist a subsequence converging to S.
Yeah, so the assumption that Sn does not converge to S basically is equivalent to saying that there exists some other subsequential limit besides S, right? Like if you say, okay, let me so if you say that, like, suppose Sn does not converge to S. Okay, so there are a lot of things that can happen, right? It's possible that Sn could converge to a different number, right? If Sn converges to a different number, then it's like pretty obvious that we have a contradiction, right? Because then literally any subsequence of that will only have subsequences converging to the other number, right, besides S. So, and then like Sn could diverge to plus or minus infinity. Those are like similar cases where it's like any subsequence will have to diverge to plus or minus infinity. So that's a problem, right? So let's suppose that Sn just like say Sn just diverges, period, right? Then there exists a subsequence of Sn converging to T for some T not equal to S. Okay.
Wait, how do we know that?
Because if there weren't a subsequence like that, that would mean that the only subsequential limit of Sn is S. And we've shown that that means that Sn converges to S, right? Like diverging period just means that like there's more than one subsequential limit, basically.
Why can't the set of subsequential limits be empty?
That's a theorem in the book and in the lecture, yeah. But the reason is that, well, either the sequence is unbounded, in which case either a plus or minus infinity is a subsequential limit, right? Or the sequence is bounded, in which case the Bolzano-Weierstrass theorem says there's a convergent subsequence.
Is it possible to approach this just using lim sup and lim inf? Like, just pick
I mean, that's actually effectively what we did before. Oops. Because by showing that, like, okay, so you're saying you'd end up showing that like the lim sup equals the lim inf, probably?
Basically, I just said that, like, since we know every subsequence of Sn has a every subsequence of Sn has a subsequence converging to S, then I can just pick the two that, like, one converges to the lim sup and one converges to the lim inf.
Yeah. Yeah, and then that'll show that the lim sup and the lim inf are both equal to S.
Yeah.
Yeah. I mean, that's like, that's a perfectly good approach. And I will say that it's like, it's only like cosmetically different from what we did before, I think.
Okay.
Like just in a philosophical sense, they are like kind of the same thing. Yeah. Mm-hmm.
Oh wait, I actually have a question. So like in terms of this, the approach that we mentioned just now, so are we arbitrarily choose lim sub, like to make the convergent limit one equal to lim sub, the other equal to lim min?
Mm-hmm.
Oh.
Can
we do that?
Yeah, well, you can say like no matter what, right? For any sequence, there has to be a subsequence converging to the lim sub and a subsequence converging to the limit. That's just always true, basically.
Okay.
So then you can just look at those as like special subsequences of the original sequence, and then try to apply this like hypothesis to those subsequences, and then that'll show you that actually like the lim inf and the lim sub both have to equal S, basically. Yeah. Okay. Mm-hmm. Any more questions? Okay, so I gotta go, but yeah, I hope this was helpful. And you know, try not to stress too much about the exam. You know, just like I said, just do your best, and remember also like this is still just the first midterm, so like no matter what happens, you're not gonna. I don't think you're gonna do like irreversible damage to your grade in this class just on this midterm. Okay, so think about this midterm actually as like more of a learning opportunity than anything. I think that's my opinion. But yeah, anyway, so I'll see you guys soon.
Thank you so much.
Yep.
Thank you.
Thank you.
Bye-bye.
Thank you. Bye.